This is Physics Lab 2, Modeling Gravitation. The purpose of this lab is to compare a computational model of gravity to an observed experiment where we consider the effects of gravity, or we consider the effects of drag, and we ignore the effects of drag. The lab focuses on the fundamental principles of the gravitational force and Newton's second law, which is change in momentum equals net force times time. We use Newton's second law in conjunction with the position update formula to create the data and the graph that we ultimately see later. This lab shows that gravity is more accurately modeled with drag than without drag in a real-life scenario. The system that we use is the plastic bag, and the surrounding is everything else, especially air and earth, since we're considering primarily gravity and drag. The shape of the plastic bag does change during the lab as it falls down, starting really crumpled up and getting a little bit bigger, which affects the drag, causing some error between the predicted data and the observed data. The pink data is the observed data, and the green is the model with drag, and the orange is the model without drag. As you can see, the model with drag is much closer to the observed data than the model without drag, but there is still some slight discrepancy between the two from the errors I discussed earlier. The physics behind the lab is the gravitational force explains the change in velocity that we see, with it acting in the negative direction as m times g. The system starts at rest, and then it continues to increase its velocity to a certain point, terminal velocity, because of gravity and because of drag. And as I just said, gravity is not the only force we need to consider because drag acts in the opposite direction of the movement and is dependent on velocity. The two forces together create a much smaller F net in the down direction, where it's still going downwards, than if gravity were the only force. As we can see here, like I just discussed, we have to consider gravity and drag. This is the code we created to create the two models right here, where we initially consider a velocity from rest, its height, the ball's mass that we measured, gravity, and then down here in line 51 we have a drag constant, and in the loop we can see we calculate speed and the drag force and the gravitational force in order to update velocity and position. When we model only gravity and don't include Fnet, and don't include the force of drag in Fnet, we don't use FD and everything else stays the same. So, as we can see here, with the top graph being gravity and drag and the bottom graph being just gravity, the only model that shows a terminal velocity is the model with drag. That's because terminal velocity happens when drag and gravity become the same magnitude and end up canceling out for F net equals 0. And if there's no second force to counteract gravity, there's not going to be a terminal velocity. So the ball being thrown downward would not change terminal velocity because drag is dependent on velocity. I'm sorry, there's a typo. And drag is dependent only on, in this model, velocity. So as starting velocity changes, the drag's going to change too, and the terminal velocity is going to end up being in the same place that it was in this scenario. Thank you for watching.